All right, let's get started. So today we're going to continue our discussion on value functions from last Wednesday. A few logistical notes first. Homework 2 is due on Wednesday, so please make sure to get that done. And then the project proposal is actually due about 4 weeks from now. So I know that seems like a long time, but before that you have to form your groups. You have to come up with a topic for your project and get that written up. So good idea to start thinking about this early. Today's lecture. We're going to continue from last week, and we're going to talk about how we can actually make Q-learning work with deep neural networks for real. So on Wednesday, we left off with somewhat of a somber note about the non-convergence of value function methods, but today we're going to have a sort of a more positive outlook on things. We're going to take kind of a generalized view of Q-learning and fitted Q iteration style algorithms and discuss how different practical methods might fit into this generalized view. We'll talk about some tricks and some techniques that we can use to improve the performance of Q-learning in practice. And then we'll discuss how Q-learning style algorithms can be used with continuous action spaces. So the goals for today's lecture will be to understand how to implement Q-learning so that it can be used with complex function approximators like neural networks, and understand how to extend Q-learning to continuous action spaces, and also how to improve performance of Q-learning in practice. OK, so let's recap from last week. Last week on Wednesday, we went through a number of techniques we could use where we directly learn value functions or Q functions without explicitly representing policies. And in particular, we covered a number of algorithms, including policy iteration, value iteration, and so on. But the two particular ones that we'll focus on today, they're all kind of variants of this fitted Q iteration or the online Q-learning algorithm, which are really kind of the same thing. So just to remind you, in both of these algorithms, the essential underlying idea is that we're trying to estimate the Q function. The Q function is the expected reward that you will get if you take a particular action in a particular state and then follow your policy. And we talked about a few ways to estimate Q functions. Kind of a very general way is this fitted Q iteration algorithm up here, which involves collecting some data, constructing target values, and then regressing onto those target values. And we talked about how the way that you collect this data, you can use whatever policy you want, although in practice, it would really be helpful if the support of that policy sort of covers the space of states and actions you expect to see. And then starting with this fitted Q iteration algorithm, we worked our way down to a completely online version of Q-learning, where you actually do all these things in a loop one step at a time. So you take one step with some policy, you compute the target value for that one step, and then you compute a gradient update with that one target value, and then you repeat. So this is a fully online algorithm. There was a question?
Yeah. What exactly is the target value again?
The target, so in Q-learning, you're trying to find a Q function. And you optimize that Q function via a regression objective. So that's the thing that's shown here. And the target value is the thing that you're regressing onto. So when I say target value, all I really mean is it's kind of an informal term for this thing. It's the reward plus the next value. Yes?
And so you're doing like a maximization of Q in step 2. So
Yes?
how do you, so isn't that an optimization in itself?
Well, so if the action space is discrete, then the way that you can perform that maximization is just evaluate the Q function for all the discrete actions and then take the biggest one. We'll actually talk about the case of continuous actions at the end of today's lecture. OK, so this is what we covered last week. And one of the things that we concluded on at the end when we talked about the theory of value function learning is that, unfortunately, for both of these methods, when the Q function estimator, this Q subscript phi, remember that phi are the parameters of your function approximator like neural net weights, if that function approximator is, unless it's a full table of values, if it's some kind of function approximator like a neural net, then in general, convergence of these things is not guaranteed. So that's a fact of life. That's not something that we can actually fix. So we won't have a convergence guarantee for these methods. But what we will talk about today is how we can get convergence in practice most of the time on a good day when the stars align and so on. And there are some things, you can't guarantee a victory, but you can take some steps to try to increase your chances. And in practice, your chances can actually be very good for a lot of really interesting practical problems. So all is not lost, and in fact, in practice, very little is lost. OK, so that's what we covered on Wednesday. So when we left off, we talked about a few of the things that are wrong. So we talked about the theory for why we can guarantee convergence, but there's also, we can take a more pragmatic view and look at, what is it about this online Q-learning algorithm that is actually kind of problematic? And there are basically two concrete things. One is that it's not gradient descent. So remember, the reason it's not gradient descent is because of this term. So your target values actually do depend on your function approximator, but you're sort of, you're closing your eyes, pretending like it's not a problem, and doing regression anyway. So that's a little bit messed up. We need a solution to that. And there's another problem, which is when you have this fully online algorithm, what you're doing up here is you're sampling some data, and then you're computing a gradient step on that data. The trouble is that if you do this all in a loop, just like we talked about with online ActorCritic, with online Q-learning, your gradient steps are all very strongly correlated. So the thing that you see tomorrow is likely closely related to what you saw today. So the thing you see at the next time step is going to be strongly correlated with the thing you see at the current time step, which sort of breaks a very standard assumption in stochastic gradient descent algorithms that your batches are actually decorrelated from each other. And this can cause some problems that I'll get into in a second. So I'll talk about first how we deal with this correlation problem, and then I'll talk about how we deal with this not a gradient descent problem. So let's start with the correlation problem. We saw this when we talked about online ActorCritic also, that basically you get some data and then you take a gradient step on that data, and then you get some more data and then you take a gradient step on that. And this time step to time step, this data point is going to be strongly correlated. When we talked about, so sequential states are strongly correlated and the target values are always changing. So the intuition behind why this is a problem is, let's say that let's forget about RL for a second. Let's say I'm doing regression onto like a little sinusoid. So this is the x-axis, the y-axis. Normally, if you're solving a regression problem, you get a bunch of IID sampled points, and you use those for your regression. But if instead what you do is you first observe some points at the beginning of the sinusoid, then you observe some points over here, then over here, then over here, and so on. And each time you observe some points, you take a gradient step. So what's going to happen if you do it that way is that on this step, you'll sort of overfit to this little local region. On this step, you'll overfit to this region. On this step, you'll overfit to this region and probably forget whatever happened over here and so on. So if you don't get these points IID, if you actually get them in this spatially correlated way, you might not ever actually learn the entire sinusoid function. You'll kind of locally overfit to each piece of it and then forget all the other pieces. So that's the intuition behind the problem with correlated samples. And we saw this also with ActorCritic, and with ActorCritic we saw that parallelism was actually one of the ways that we could address it. And we can do the same thing for Q-learning. So just like with ActorCritic, we had this scheme where you have multiple threads that run, you collect multiple independent samples from these threads, take a gradient step on those independent samples, collect more samples in parallel, and so on. And then you could do this asynchronously also. So all the same stuff that we had before for ActorCritic, this is exactly the same picture as before, you can do for Q-learning as well. And that will help you decorrelate your samples. But that's not the only solution. So does anyone have any questions about this, in particular about why correlated samples are a problem and why the parallelism stuff can allow us to address that problem? OK. So parallelism we already knew about. That was a couple weeks ago. There is actually, with Q-learning, another solution, which sometimes is better, because if you're doing this parallel stuff, it's fine if you have a simulator and you can spawn off multiple threads of your simulator. But if you're doing Q-learning on a real physical system, let's say you're controlling, I don't know, some kind of parameters for a heating and ventilation system for a server farm, running 5 server farms in parallel is rather onerous. It'd be awfully nice not to have to do that. So with Q-learning, there's another solution that we can use which takes advantage of the fact that Q-learning is off policy. Remember that off policy means that the data that's used in this update over here doesn't have to come from the same policy as the one that we currently have. And that is a difference between Q-learning and the ActorCritic method we covered before. So for ActorCritic, the parallelism was a preferred solution. Here, there's actually another solution that in many cases is better that exploits the fact that this is an off-policy algorithm. This is sometimes referred to as a replay buffer. So the idea is this. Let's go back to the full fit acute iteration algorithm, because there it's a little bit easier to illustrate. And with the full fit acute iteration, and the reason I'm going back to it is because this is just a special case of this with k equals 1. And remember that any policy here will work, provided it has broad support. So what we can imagine doing is we can even just say, let's not collect the data in step 1. Let's just completely cross out that step. Let's say that we collected a whole bunch of data before, and we just put that into our database. And now we're just going to keep pulling from that database to make these updates. That's still perfectly fine, because this quote-unquote policy that goes into that database and makes a query is every bit as good as any other policy you could use, provided it has broad enough support. So since we don't care about what policy the data comes from, it might as well just come from a big bucket of previously collected data that we just put on our hard drive or something. It doesn't have to be a policy that's actually interacting with the simulator. So just load data from a buffer for these steps 2 and 3 and just keep oscillating between these two things. And that's according to the theory, that's not any better or worse than collecting new data in step 1. So this is the view of fit a queue iteration that we had before, where you just have this big bucket of transitions. Who cares where they came from, provided they cover the space broadly enough, and you just keep crunching on your fit a queue iteration in there. And you can do exactly the same thing up here. You can just say, OK, let's omit the step 1. Let's, instead of actually taking some action and observing some transition, let's just pull that transition out of a database of transitions we had before, out of this bucket, and just take the steps. And that's perfectly fine. Of course, in practice, your performance depends on those transitions adequately covering your space, but it's not any better or worse than any other policy in principle. And then you can still do this one gradient step here. So in fit a queue iteration, this is a full minimization. In the online version, it's just one gradient step. Fine. It's all the same. So in practice, queue learning with a replay buffer can work like this in the kind of the simplest version, where we're not even collecting any more data. We just replace the step 1 with a step that samples a batch from your buffer B. And the nice thing about having a buffer is that you can sample an entire batch from it. So not only have we gotten rid of the correlation, we can also actually compute this gradient by summing over multiple data points instead of having just one data point. So you have your big bucket of transitions, sample, let's say, 64 transitions from that big bucket, compute your gradient, averaging over all 64 of them, and take your gradient step. And that'll decorrelate your samples, and it will also give you a lower variance gradient, because now you have a batch size that's larger than 1. So samples are no longer correlated, multiple samples in the batch, which gives you a lower variance gradient. But of course, we have to get the data from somewhere. So if we're lucky enough to have some magic oracle that just gave us a bucket of really awesome data, then we're very happy with that. But it would be really nice to put back somewhere into this loop a step that actually does add to that buffer and collects more data. Because in practice, for very large spaces, it may be very difficult to have a support that covers the whole space. Maybe the best we can do is hope to cover the space where we'll actually visit. And that does require us to get a little bit of data that's sort of in the vicinity of where our policy will actually go. So now, let's put that step back in. So we need to basically feed the replay buffer. We need to keep replenishing it with sort of fresher data so that we make sure that the support of that data set covers the states we'll actually visit with our policy. So we need to feed our replay buffer. So what we're going to have is we're going to have this queue learning thing that's going to crunch on the data in this bucket. And then we'll have our policy will grab the thing from here, interact with the world, and bring back some more data. And we can actually do these things in parallel. We can actually parallelize them. But I'll introduce a simpler algorithm later that doesn't do that. But in principle, you could even parallelize this thing. You can have one thread that's interacting with the world here, periodically replenishing your replay buffer, and another thread over here that's pulling things from the replay buffer and using that to update your queue function. That's perfectly fine. And most of the time, if your replay buffer is big enough, this thing here won't even be pulling the latest data. It'll just be pulling something that's sitting there in your database. OK, so that's kind of the schematic view of replay buffers. This thing doesn't care that the data is off policy, and this thing will periodically replenish the replay buffer to make sure the support of your data set covers the states you'll actually visit with your policy. So if we put it all together, if we want to construct sort of a simple queue learning algorithm with a replay buffer, we can do it like this. In step 1, we collect some data using some policy and add it to our buffer. That's this part. Then in step 2, we'll sample a batch from the buffer, and we'll take a gradient step to update our queue function on that batch. And maybe we repeat this thing k times. And after k times, we jump back out and repeat the whole thing. And k equals 1 is the most common choice. But actually, larger values of k can be more efficient if data collection is very expensive. So if you have a large replay buffer, but it's very expensive to get more data from the real world, maybe it involves running a real physical system, then taking a few more gradient steps in between each sim step might be a good idea. Or you might even split them up into 2 separate threads. But if simulation is relatively cheap, you might just set k to 1 and just crunch on it that way. So this is kind of a simple synchronous version of this algorithm, where it goes to the world, grabs more data, chews on that data a little bit, then goes back to the world. Does anybody have any questions about this method? OK. So we've dealt with this correlation issue, right? We said, if we don't want to have to worry about the samples being correlated, let's use a replay buffer, which means let's have our queue function train on previously collected data, and let's periodically replenish that data by collecting some data using our policy, for example, an epsilon greedy policy. Now, we still have to deal with this other problem, with the fact that it's not gradient descent. This is all this non-convergence stuff. So all the non-convergence stuff we talked about, that isn't fixed with the replay buffer issue. It has nothing to do with that. It's just because of these nasty target values. So let's deal with the non-convergence issue. One of the things, kind of the intuition behind how we can deal with the convergence issue is to compare Q-learning to regression. So when I write out Q-learning like this, it's not quite apparent why it's a regression problem, but when I write out the more batch mode full fitted Q iteration algorithm, you can see that this, this step right here looks an awful lot like a regression step. And in fact, this thing here is just one gradient step for that regression problem. It's just that when you take one gradient step and then grab new data, you're sort of trying to hit a moving target. Whereas down here, you just create this regression problem. You solve that regression problem. That's guaranteed to converge, but then you recompute your targets. It's still, there's nothing kind of qualitatively different between the top and bottom, and the bottom is not any more guaranteed to converge than the top. It's just that the bottom one, at least this step down here, step 3, that one is guaranteed to converge. It's just the whole thing might diverge. So somehow, taking these gradient steps on this kind of fixed target is a little more regression-like, and it's maybe, in practice, a little more stable. So this is a perfectly well-defined stable regression, although we haven't actually bought ourselves any guarantees about the whole algorithm. So what we can do is we can actually take that Q-learning algorithm and we can make it more regression-like to improve its stability in practice. It won't buy us any guarantees, but it'll make it quite a bit better in practice. So what we can do is we can say, OK, we're going to collect our data set. We're going to sample the batch. And I think there's something a little screwed with my slides. There we go. OK, let me just write out this whole thing. So what we'll do is in step 1, we'll take our whole, and I might as well finish this. We take our whole parameter vector, and we save it out to a vector of parameters that we're going to call the target network parameters. So we'll just put them away in a locked box, and then we won't touch them. We put them away in this locked box. And then we do the usual stuff. We collect our data, we sample the batch from the buffer, and then we'll compute a gradient step. We'll use these stored parameters for the target. So the stored parameters here aren't changing. They were put in that locked box where they're not allowed to change. So now the target value, it's not actually a moving target anymore. These parameters are fixed, and only these phis are changing. And then periodically, much more rarely than we go around in this loop, periodically we'll actually update phi prime to be equal to phi. So the idea is we're still trying to hit a moving target, except that now the target is not moving quite so quickly. So we'll save out our target network parameters, put them in a box, lock it, take some gradient steps, improve our network, and then we'll take it out, we'll update them again. And then we do this more. So this way, this inner loop here looks a lot more like standard supervised regression, and the potential for the target to change only occurs when we pop all the way out to this outer loop and update our target network parameters, which happens much less frequently. So qualitatively, as far as the theoretical guarantees, we haven't actually changed anything. So we didn't have guarantees before, we don't have them now. But in practice, this tends to go a long way towards actually stabilizing the algorithm, because even though we're still trying to hit a moving target, it's moving much more slowly now. So the target doesn't change in the inner loop, and this thing looks like supervised regression at steps 2, 3, and 4. So now, yes, there's a question.
Can this also affect the speed of convergence if it converges?
Yes, of course. So the price that you pay for this is that everything takes a lot longer. Here's a thought exercise to help understand why. Let's say that you initialize your target network so that your Q values are very small, close to 0. That means that the first time you go around this loop, this value kind of vanishes and you're mostly regressing onto rewards. So if, let's say, you update your target value, your target network, about every 10,000 steps. That's a pretty typical number. If you update it every 10,000 steps, then for the first 10,000 steps, all you're doing is memorizing rewards. For the next 10,000 steps, all you're doing is memorizing reward plus next value. For the 10,000 steps after that, you're going 2 steps forward. So you're moving forward very, very slowly. And it kind of makes sense. Like if you have an unstable algorithm, if you have something that might diverge, slowing everything down, damping it, will increase your probability of things converging. So you're essentially just trading off speed for better convergence. So now that we've introduced replay buffers and target networks, we can put the pieces together and write down sort of the classic deep Q learning algorithm. This is sometimes referred to as deep Q networks or DQN, which is an algorithm that uses replay buffers and target networks. And it works pretty much exactly as shown in the previous slide. So you save out your target network parameters every some number of steps. In practice, 10,000 is a good number. Actually, I guess I can go through the full code here. So you're going to take some action. You're going to add it to your buffer. You're going to sample the mini batch from the buffer. So the fact that 2 comes after 1 is sort of almost irrelevant because these steps once the buffer is big enough, these 2 steps are practically independent of each other. You sample some mini batch from B, mini batch size maybe 32 or 64, something like that. You compute the target values using the target network for every single transition in your batch, and you can do this in parallel. Then you compute the gradient and update your current network parameters phi. And then every some number of steps, you're going to update your phi prime by copying over phi. And this is where the number of steps might be about 10,000. So you can see that this classic deep Q-learning algorithm is basically a special case of this algorithm up here, where we just take one step in here, so k equals 1, n equals 1. I'm kind of overloading n here. These are not quite the same. And then this thing happens every 10,000 steps. So you're going to actually implement a version of this algorithm for homework 3. So it's a good idea to understand how that works. But it's basically a special case of this more general kind of fitted queue thing up here. Does anybody have any questions about this algorithm? Yes?
In the 10,000 steps you're saying, how does that vary, I mean, I guess with the complexity of the states of the world, of the environment, I guess?
Yeah, so the trade-off with the number of steps between target network updates is that the more often you update your target network, the faster you'll learn. Because every time you update the target network, you're essentially allowing the values to flow backwards one more time step. But also, the more often you update the target network, the less stable things will become, because in the limit, if you update every single step, then you're back to that moving target problem. OK. There's an alternative to the target network, which is also used in some Q-learning style algorithms. And to motivate this alternative, let's illustrate a little kind of, it's not so much a problem, but it's sort of something that's a bit aesthetically displeasing about how target networks function. So let's think about this step 5 a little bit. Here's a little bit of intuition. Let's say that I'm going to illustrate my learning process on a kind of timeline graphically. So I'm at a very high level, I'm basically alternating these 2 steps. I'm collecting some data, that's the blue box, and then I'm updating my phis, that's the green box. So, and I realize that these colors are the same colors I usually use in my diagram, but they're actually flipped. Sorry about that. So if you remember my diagram with the loop, this should actually be orange and this should be blue, but don't worry about that. OK, so I'm going to just alternate. This is how the process works. Collect some data, update phi. Collect some data, update phi, and just keep going like that, right? So that's all good. And then every time you update phi, you're going to grab the target network from somewhere in the past, right? Because the target network is updated infrequently, so maybe this is intentionally compressed. Usually this arrow will be like 10,000 steps long. Here, let's say the arrow is only a few steps long, right? So we're grabbing our target network from in the past back here. And then in this step, we're also grabbing it from the past, but in the same spot, because this is where we flipped the target network. This is where we wrote phi into phi prime. And then here, we're also grabbing it from the same spot. But maybe over here, this is when we hit that boundary where we write phi into phi prime. So then this step actually gets it right from the previous one. So something here feels a little bit kind of asymmetric, right? So over here, there's basically no lag. We're picking up the target network right from the previous step. Whereas over here, on just the last step, there's sort of maximal lag. It's going very far into the past to get the target value. So somehow you have this sort of pulsed update where the amount of lag, how far in the past your target values are, keeps changing. And specifically, every time you flip the target network, it's right in the immediate past, and right before that, it's very far in the past. And this feels a little asymmetric in some way. So it's weirdly uneven. Can we always have the same lag? Can we always have target values that are lagged from the current values by the same amount? So there's a popular alternative to using these target networks, which is very similar to something called Polyak averaging, if you're familiar with that from optimization. So the idea is that in step 5, instead of writing phi into phi prime every n steps, instead what you do is every single step, you do a weighted average of phi prime and phi. And specifically, you basically linearly interpolate the weights. You do some tau times phi prime and 1 minus tau times phi, and tau 0.999 works well. So that means that phi prime is pretty much entirely equal to phi prime, but there's a little piece of it that gets the latest weights. So given enough steps, eventually phi will completely overwrite phi prime, but there will be a lag, and the time constant of that lag depends on the setting of tau. So now, every single step, phi prime is lagged by the same amount from phi. Of course, you're interpolating parameters here, which is maybe a little weird. There's some theoretical justification for why this is reasonable to do, which comes from optimization. So if you want to find out about that, look up polyac averaging. OK, so this is just an alternative to making this flip every n steps. Now, one thing that I want to discuss a little bit today is how this Q-learning algorithm relates to fit-a-Q iteration. And in fact, as I've kind of alluded to before, they're kind of the same thing, that where the Q-learning algorithm is just a special case of this fit-a-Q iteration. But we can make this a little bit more explicit. So this is the Q-learning with the replay buffer and the target network at the top. And at the bottom is a kind of the fit-a-Q method. And they look very similar. In fact, the main difference is that with the Q-learning with the replay buffer and target network, you're sort of flipping your target network up here in the outer loop. And with the fit-a-Q iteration, you're doing it in the inner loop. And the difference there is actually very slight. Like if you could imagine these things actually being separate processes, and they just have different frequencies, and sometimes one is higher frequency, sometimes the other is higher frequency. So in the classic fit-a-Q iteration, this thing down here that I presented before, the equivalent of the target network is actually flipped in the inner loop because we're doing the supervised regression. So when we're doing the regression, the target network is not changing. So here I just wrote out the SGD in the regression right here, and that's it. So this part is just SGD. This is what I previously represented with that min. So before I wrote phi equals arg min phi, and now I just wrote out the SGD process in the inner loop. And you can see that it's the same exact process as the one up here. So dqn is kind of a special case of this thing with n equals 1 and k equals 1. And then fit-a-Q iteration and the Q-learning, it's just a matter of flipping the order of these two steps. So what this means is that we can actually come up with a generalized version of this Q-learning algorithm that subsumes all of these methods. And it's just a process that it's an algorithm that consists of 3 separate processes. So the 3 separate processes, they don't have to run in parallel. They can run synchronously, just with different frequencies relative to each other. And the 3 processes are the following. The first is the process that populates your replay buffer. So this is the process that takes your policy, goes out into the world, acts in the world, maybe with epsilon greedy or some other exploration strategy, and it brings back your transition tuples. And it takes those transition tuples and it puts them in your replay buffer. Now, if it does this for long enough, your replay buffer will get really big, so something needs to go in the trash. So if you, like one very standard strategy to use here is to just say, let's evict the oldest data. Let's make the replay buffer a ring buffer, and when we fill it all up, then the oldest thing gets evicted. That's a very standard thing to do because probably the oldest thing is the thing that's sort of least good. That's where you were running your crappy old policy. So let's evict that. So this is the process 1, the data collection process. It always takes whatever is your latest policy, goes out into the world, brings back your transition tuples, and uses them to replace the oldest transition tuples in the replay buffer. Process 2 is the process that's going to deal with the target network parameters. So it has these 2 buckets, the target network parameters and the current parameters. And all it does is it copies over phi into phi prime, or polyac averages them, with some frequency. And typically, this process 2 has a pretty low frequency if you want to keep things stable. And then there's process 3, which is the actual learning process. So process 3, it pulls in the target parameters, samples a batch from the replay buffer, updates phi, and puts that back in. So all it does is it takes these 2 things and sticks them out there. And that's process 3. So process 3 is the only thing that's actually doing any learning. And then all of these different Q-learning algorithms, whether it's fit-a-Q iteration, dqn, whatever, they're just instantiations of this with different choices of frequencies for process 1, 2, and 3. And you can imagine running them in parallel. You can imagine running them synchronously. You can imagine choosing many steps here, just a few steps there, whatever you want, depending on the relative cost of data collection, neural network updates, and your desire for stability in regard to process 2. So this is sort of the fully generalized view of all of these Q-learning style methods. Does anybody have any questions about this? Yes?
I have a question about collecting data for transitions. So when a robot has absolutely no idea of what to do, like what state do you put it in? You just like parachute it into some kind of random state?
Yeah. So there's 2 parts to this question. One is, how do you choose the states when you're collecting data? And the second one is how do you choose the actions when you have no idea what to do? So typically, the choice of states is not actually up to you. It's up to this thing. It's up to the world. So every time you ask the world, I want to act. I want to use my policy. It puts you in the initial state, and then it lets you perform a trajectory. So you don't get to choose that. You do get to choose how to act. You're completely right that in the early stages of training, this policy won't have any idea what to do. And in fact, in practice, what we typically do in Q-learning is we actually, remember that the epsilon in epsilon greedy exploration, the epsilon controls how much on policy we are. We typically start off with a bigger epsilon, and then we gradually reduce it. Because early on, the policy is so bad, we might as well act randomly, and then we'll gradually become more deterministic, and we'll gradually follow the Q function more and more as the Q function gets better. So that's a very common heuristic for this. OK, so let's talk about how the different instances of the algorithms we learn about are kind of special cases of this broader picture. So the online Q-learning is not the thing we covered today. That's the thing we covered last week. The fully online Q-learning evicts immediately, which means it only stores one sample in here. And process 1, process 2, and process 3 all run at exactly the same speed. So it takes one step on this, one step on this, one step on this, and immediately evicts whatever's in the replay buffer. So it's fully online. It's not storing any data. That's the online Q-learning. DQN, which we covered today, process 1 and process 3 run at the same speed. So for every step of data collection, you take one step of Q function regression. Process 2 is pretty slow, and your replay buffer is big. So that's DQN. And then fit a Q iteration. In fit a Q iteration, process 3 is actually in the inner loop of process 2. So you crunch on this a little bit, then you update network 2. And this whole thing is in the inner loop of process 1. So that's fit a Q iteration. So all of these methods are basically special cases of this more generalized kind of scheme for Q learning. All right, so now we're going to take a 3-minute break. So we'll come back in 3 minutes. And if any of you guys have anything you want to ask or discuss, feel free.
Would it make sense to, since the samples are actually, correlated because they're drawn, from a process, wouldn't it make sense to throw out every third sample or
So in practice, usually if you're evicting old data and you're keeping a replay buffer, the size of the replay buffer is very large. It's like 1 million samples or something like that.
Right.
So the fact that you're throwing out the old data doesn't really increase the correlation. If you let's say your episode lasts on average maybe 100 time steps, and you're keeping 1 million steps around, almost all randomly sampled batches will be decorrelated.
That makes sense. Okay. But I guess. All right. Yeah. Okay. Cool.
Mm-hmm.
Is there a difference between fitted and fully fitted?
No, I think it's just a sloppy terminology on my part.
Oh.
Yes. Sorry.
So, in the active critic algorithm, when you feed the baseline, you only feed it to the new samples, or you just do a few upgrades.
So in actor critic, it's fitted to the latest samples because you need data from your latest policy to do that.
Okay.
So this is not an off-policy fitting step. This is actually on policy. So that's why all this stuff with replay buffers we didn't even talk about it for actor critic because they're on-policy algorithms.
So you don't reuse the old data.
That's right.
Okay.
I mean, there are ways to do it. There are sort of extensions you can do, but for the version that we covered in class, it's fully on policy.
So in the homeworks, we have to reinitialize the weights for the baseline.
You don't necessarily need to reinitialize the weights. You just have to use only the latest data. What you do with the weights is a separate question.
So we can reuse the latest weights, but we update it with the new data.
Right, because you need data that actually came from the policy for which you're fitting the values. So the data needs to come from whatever policy you're trying to evaluate.
I see. But the weights, it also reflects the effects from the old data, right?
Right, so if you run SGD for a small number of iterations, in practice, there will be sort of the residual effects from the previous time step that might exacerbate some instabilities. In practice, people usually kind of ignore that problem, but it depends on how many gradient steps you take and how much data you have and all these other factors. Okay, let's continue. Was there a question back there? So the question is, can you do something similar for actor-critic algorithms? The trouble with actor-critic algorithms is if you're trying to estimate a value function rather than a Q function, you actually need the transition to come from your policy. You can do actor-critic with Q functions instead of value functions, in which case you can train them actually off policy. There was I think I very briefly mentioned a reference to an algorithm called QProp that actually does exactly this. It uses a replay buffer to train the Q function, but it trains it as a critic for an actor-critic algorithm. So that's an option, but then you have to use Q functions rather than value functions. Yes?
From online learning, if we make data immediately, we still get the problem of the data being very complicated.
Yes, so this online Q learning algorithm from last lecture, in practice, if you use it with deep networks, oftentimes you won't get very good results. So if you want sort of as online as possible with deep nets and Q learning, probably this would be a good choice. Okay. So now that I've kind of introduced and described the kind of Q learning algorithms that we might actually want to use in practice with deep neural networks, let's talk about a few extensions and improvements, some of which actually make a really big difference. So the first extension or improvement is going to deal with this question. Are the Q values actually accurate? Right? So Q values have a certain meaning. Q values estimate the expected reward you will get if you take a particular action in a particular state and then follow your policy. But when you run these algorithms, when you run, let's say, DQN, do you actually get Q values that reflect the actual rewards that you will then see? So these are some plots from Q learning, basically the DQN algorithm being used to learn to play a few Atari games. Test? Oh, yeah, that sounds better. Thank you. OK. So,
Sorry, I can't see from here. Do the values on the y-axis agree as well between the?
no, they don't. And that's what we're going to talk about next. So both of them are going up, which is good. So as predicted Q increases, so does the return. The trouble, and we can analyze this a little bit more. We can actually look at some nice pictures. So here, this bottom plot actually shows the value function. So this is just maximizing over the actions. And the top plot shows screenshots from the game Breakout. So those of you that are not familiar with the game, the object of the game is to hit a ball with this paddle down here and cause it to break the bricks. And if you're a real pro at Breakout, what you're going to do is you're going to punch a little hole through the bricks, and you'll hit the ball so that it goes on top here and bounces around and kills all the bricks. And you only do that if you're really cool. So what this plot is showing is that, well, as this guy hits the ball and it bounces around and hits the bricks, it predicts a little spike in value right before the brick is going to be broken because it's going to get a reward. So it's happy about that. And right here, as it sees itself punching this hole, the values start going up. It's anticipating the reward that's going to come, right? And then right here, once it sees the ball is actually going through here, the value is at its highest peak because now it knows it's going to get all this big reward from having the ball bounce around up there. So that all makes sense. It seems like the reward really reflects the kind of things we expect to see. If you do an experiment with a monkey and you give it juice, it'll anticipate the juice, and your Atari playing bot will anticipate the breaking of the bricks. So that's good. Here is Pong. Here we're going to look at the values of different actions. So this is just the relative values of actions. The cyan one means stay in place. This one means to go up, and this one means to go down. And you can see that the ball is over here, far away from the paddle, and it says all the actions are reasonably good, but the one to go up is the highest. The reason they're all reasonably good is because it knows that even if it accidentally goes down, it can still recover by moving up afterwards. So it knows the ball is far enough away that even if it makes a mistake now, it can still recover itself. Here, the ball is a lot closer, and it's saying, oh, I definitely need to go up, because if I go down now, I'm in trouble. This is the time to go up. And here, same thing. And then here, you can see the ball is, it's about to score a goal on the opponent, and all the values are about the same for all the actions because it says, okay, it doesn't matter what you're going to do, you're going to win anyway. So values seem to make sense qualitatively. The relative values of actions seem to make sense. Everything is good with the world. But now we can actually look at the numbers, and that's where we start getting in trouble. Ignore all the blue stuff for now, just look at the red stuff. So here what you're seeing, this kind of jerky red thing, that is the estimate of the Q value from the neural network. The horizontal red line is the actual expected reward that the policy will get here at the end. So what you'd expect to see if it's estimating the rewards properly is that the red line should be tangent to the curve at the very end. So it should go like this. But instead, the red line is way down here. In fact, this is systematic. Across all of these games, the estimated Q values are substantially higher than the actual returns, which means that the Q function is actually overestimating how good it's going to do. It thinks it's going to do really well, and then in practice, it systematically does substantially worse. It's still improving, but it's just not estimating the right numbers. So why is that? So there's kind of a little bit of a heuristic argument for why we should expect to see overestimation in these kind of Q-learning algorithms. And the argument goes like this. So our target values, they're maximizing over actions. So they're basically evaluating different actions for the next state and then taking the one with the biggest value. So the problem is this max. So here, as an aside, let's imagine that we have two random variables, x1 and x2. The expectation of the max of these two variables will always be greater than or equal to the max of their two expectations. Essentially, when you take the expectation of the max, you're taking if you imagine these two variables have some mean corrupted by some noise, when you take their max, you're sort of amplifying the noise. You're saying, find me the value where the noises of the two are biggest. So when you take the expectation of their max, that's going to give you a bigger value because you're maximizing over the noise. And that's essentially what's happening up here. So if you imagine that your Q value is not perfect, it kind of looks noisy. So it's sort of close to the true Q value, but corrupted by some noise. When you maximize over the action, you're essentially amplifying that noise. You're taking the action for which you have the highest value, which might be highest just because it has the most noise. So for this reason, whenever you do this max, it's going to overestimate the next value. So if you have some action for which you accidentally, just due to noise, assign it a higher value, you're going to use that, and then you'll just keep building on it. So you'll keep amplifying that noisy max. Now, one of the things that we can look at to better understand this is to actually write out this max in this funny way. The max of the Q function with respect to the action A prime, you can write it out as the Q value at the next state and the action given by the argmax. This is sort of a silly way to write it, but it makes it clear why this problem exists, right? If there's some action for which you have an erroneously large value, you're going to pick that in the argmax, and you're going to evaluate its value, which will be erroneously large. So when you select your action according to the same network as the one for which you evaluate the value, you're going to amplify the noise. So the value comes from Q phi prime, and the action comes from Q phi prime. So one of the ways that we can address this issue, this is a method called double Q learning, is to not use the same network to evaluate the action as the one that we use to pick the action. So the value we evaluate according to one network and pick the action according to another. So if the noise is decorrelated over here and over here, basically if this value is corrupted by noise and this value is corrupted by noise, but the noise itself is not correlated, then the problem goes away once we decorrelate the noise of the action selection mechanism and the action evaluation mechanism. So one of the ways that we can decorrelate that noise is we can just not use the same network, both choose the action and evaluate it. So in double Q learning, the reason it's called double is because there's two networks. You have one network, let's call it phi A, and that network phi A is updated based on the value that comes from phi B for the action that comes from phi A. And vice versa. Phi B is updated according to the value from phi A, but the action from phi B. So because now the value and the action selection mechanism are noisy in different ways, now the noise won't actually be amplified when you compute your target values like this. So if phi b erroneously picks an action for which it's big due to noise, that action was probably not going to be big due to noise for phi a because it has different noise. So you'll actually get a lower value. So if you can decorrelate the mechanism for evaluating the action versus from the mechanism for choosing it, then this problem can be mitigated. So we need two networks in order to do this. Which networks do we use? Well, we already have two networks because we have this funny target network thing lying around. So let's just use that. So in practice, what we can do is just use the current and the target network as the two networks for double Q learning. So in standard Q learning, you compute your target value like this, where phi prime is your target network. And in double Q learning, exactly the same. The only difference is that now you use the current network to pick the action and the target network to evaluate it. And that's it. So you're just going to use the current network rather than the target network to evaluate the action. We still use the target network to evaluate the value. And the problem can actually be mitigated to a very large degree. So this is a very, very simple change to the standard Q learning method that I covered before. And in practice, it actually tends to substantially improve the performance of this algorithm. Does anybody have any questions about double Q learning? Yes?
Can you be, is it the case where the two networks would predict a different optimum action?
So you can't, I guess what you're kind of getting at is can you be sure that this really decorrelates the noise? And the answer is you can't. So we have sort of this kind of somewhat aesthetically attractive idea over here that, yes, if we have two different networks, they're decorrelated and everything is good with the world, and then we sort of just did this kind of hack here to actually put that into action. It's not, like, there's nothing that guarantees this actually being right. But hopefully if you lag your target network enough, they'll be somewhat decorrelated. And in practice, it actually does seem to help quite a bit.
I guess I can, okay, yeah.
Yes?
Does the correlation kind of spike up every time you update your phi values then?
Very likely, yes. So I'm not aware of any studies that have actually looked at whether, for example, polyac averaging versus flipping every n steps actually makes a difference in regard to the performance of double Q learning, but it's very possible something like that might be the case. Yes?
Since we only take one sample for the next step, but since we have all the database, can we just collect multiple samples independently and just average them for the next report?
You can do that, but it doesn't actually address the overestimation problem. The overestimation problem is not due to a max over samples. It's due to a max over actions. So you would always evaluate all of the actions for each of your samples. So the answer is you can do it, but it won't fix the problem that this is addressing. OK. Oh, there was another question?
Yeah, so does double Q learning depend in some way on the initial conditions for the two networks, phi prime?
That's a good question. The answer is I don't know. So in practice, people typically initialize phi and phi prime the same way. I suspect that if you're actually going to copy over phi into phi prime, which is sort of the standard thing to do, it actually won't matter because even if you initialize them differently, the first time you copy phi into phi prime, it'll just override whatever you did there. So it likely won't make a difference. I don't have a strong intuition for what would happen with polyac averaging. I expect that there it won't make a difference either because after a while, phi prime will just be replaced by phi. OK, let's talk about multi-step returns next. So in Q learning, our target values, and I'm going to intentionally put subscripts T on everything, and you'll see why for a second. So our target values are given, obviously, by the reward plus gamma times the next value. And where does kind of the learning signal here come from? You know, your target value is sort of composed of two parts. It's composed of a reward part and a Q part. And if you have sort of a long horizon problem, and your Q values are pretty good, then almost all of your learning signal sort of comes from here. Like this R is comparatively pretty small to the effect of this big Q. Just quantitatively, like, you know, Q is reward over many steps, R is reward for one step. So if you have pretty good Qs, almost all of your sort of supervision signal when you do that regression comes from that second term because that second term is just bigger. But if your Qs are not so great, if you're just in the early stages of learning and your Q function is terrible, maybe you initialize it maybe so that it's a small random number, then it's mostly the R's that matter. So in the early stages of learning, if your Q values are bad, mostly the R's are the thing that you're learning from, and the Q's are just contributing noise. So if the Qs are should be responsible for more of the learning because they have bigger magnitudes, then in some ways this kind of target is not great because you just have one reward and then everything else is the Qs are responsible for that. When we talked about actor critic, we had this nice discussion of variance and bias. So if you remember this picture for actor critic, we could estimate the critic value by taking the reward plus the next value minus the current value, or we could take it by adding together the rewards. And we talked about how this version where you use the values, that version has the lowest variance because you don't have the single sample estimator, but it has the highest bias if your value function is wrong. And this version, the kind of more classic reinforced version, has no bias, but it has higher variance because you're essentially estimating a big expectation with just a single sample. So if you're back in actor critic land, if your value function was bad, you're probably better off using this thing because then you get that big sum of rewards and you don't have to worry about bad actors, bad critics. And we talked about how you can actually interpolate between these two. So you can say that, well, in the intermediate stages, if your value function is kind of OK, maybe you add together a bunch of rewards for some number of time steps, and then at the end you put your value. And we talked about how that might be better if your value is not so great, because at least you get multiple rewards before you put that bad value in there. So Q-learning does this version. It does the version where you take the current reward plus the next value, which is sort of the maximum bias but the minimum variance. Can we construct multi-step targets for Q-learning, just like in actor critic? So when your Q function is bad, can you add together multiple rewards and then put in the Q function and learn faster that way? The answer is that yes, you can. So you can construct your target values like this. So now we're going to add up all the rewards from t to, this should be t plus n minus 1. So we're going to add up all the rewards from t to t plus n minus 1, and then we'll put in the Q value at the very end. And now the Q value is multiplied by gamma to the n. So if we have big N, then it doesn't even matter what your Q network is. All that matters is that you're adding together the rewards. So this will reduce the bias from having a bad Q function here, but it will increase the variance because this is a single sample estimator for something, for your expected reward. So this is sometimes referred to as the n-step return estimator. Q-learning with n-step returns is a little bit of a problem, though. So it's less biased. You get less biased target values when the Q values are inaccurate. It's typically faster at learning, especially early on when your Q values are inaccurate. So that's good. You can actually get pretty substantial speed up from doing this. But it's actually only correct when you're learning on policy. So remember, we made this big deal out of Q-learning being off policy. This thing kind of throws a wrench in the works. Why? Well, your policy, it depends on the Q function. So this thing is supposed to estimate the Q value of your policy, for some policy pi, specifically the one given by this equation. So that means that you need transitions that actually come from pi for all the steps from t prime minus t to n minus 1. So if n is equal to 1, then there are no problems, because if n is equal to 1, you don't need any on-policy steps. But as soon as n becomes greater than 1, all the steps before the last one need to actually come from your policy. And that gets you into some trouble if you want to do off-policy learning. So things get a lot faster because you're not as reliant on your Q value giving you most of the supervision signal, but they have to be on policy. So how do you deal with it? Well, you can ignore the problem. That is theoretically the worst solution, but in practice, it's actually like a pretty good solution. So it's highly problem dependent, but it seems to work pretty well. Not the first time that's happened. You can do what's called, you can cut the trace. So that means that you can dynamically choose n to get only on policy data, which tends to work well when the data is mostly on policy and when the action space is small. So imagine that game of Pong where you have just 3 actions: stay still, go up, and go down. It's not unreasonable to expect that if your replay buffer is populated by data that came from older but fairly recent policies, you might actually find entire sequences in that replay buffer that look like sequences that you would have taken from your current policy. So you can just, instead of choosing n in advance, you just pull up a trajectory from your old replay buffer, and then you add together the R's, so long as you're getting actions that you would have taken anyway. And as soon as you get an action that's different than what you would have taken with a current policy, then you cut the trace and you put in the max Q. So instead of choosing n in advance, you just dynamically choose n based on how many on-policy actions you happen to pull out of your replay buffer. Now, of course, as your action space increases, this becomes incredibly unlikely, and if your action space is continuous, this basically never happens. But if you have a small discrete action space, and mostly on policy data, which means that you evict fairly aggressively, this is actually quite a reasonable thing to do. And then the kind of heavy-duty solution that always gives you an unbiased answer, but is more complex for a wide variety of reasons, is to use importance sampling. So that's the same story as with policy grading when we talked about it before. If we have data from the wrong distribution, we can reweight it with importance weights and get data from the distribution that we want. Now, in practice, how you actually do importance sampling matters quite a bit, and there are a number of pretty delicate choices there. I won't get into it in this lecture, but if you're interested in importance sampling, a nice, fairly recent paper to read is called Safe and Efficient Off-Policy Reinforcement Learning by Munoz et al. So if you're interested in importance sampling, adaptively choosing trace lengths, and so on for off-policy Q-learning with multi-step returns, check out that paper for a starting point, and they'll also have citations to more canonical literature in there. So that's the story with n-step returns. Does anybody have any questions about n-step returns for Q-learning? OK. All right, and then the last part of today's lecture I'm going to use to discuss how we can do Q-learning with continuous actions. So what's the problem with continuous actions? Well, many of you might have already guessed this. So our policy pi is going to choose action, is going to basically assign a probability of 1 to the action that maximizes the Q value. So this is a max. That's the problem. The other problem is this. Your target value also has a max. And this max for the target value is actually particularly problematic because if you imagine even something like the classic DQN algorithm, it's going to take one step in the environment to collect data, and then it's going to take one gradient step using a batch of maybe 32 or 64 transitions. So this max here gets evaluated 32 to 64 times more often than the max up here, and that's in sort of the most online algorithm. If you use a fitted Q iteration algorithm, maybe you're doing this thousands of times per every max out here. So this second max in the target value is actually more problematic because it gets called much, much more often in practice. So we need some way to estimate this max. How do we perform the max? We have a number of choices. Option 1 is to do some kind of optimization. Gradient-based optimization like SGD is a little bit slow in the inner loop of another optimization process for this max. So you can do it with gradient-based optimization like SGD, but it's kind of clunky and slow. But your action space is typically low dimensional, at least low dimensional relative to the dimensionality of your network. So even if you're controlling some really complicated system with a few dozen action dimensions, probably your network has like thousands of dimensions. So the action space is relatively much lower dimensional. So this is actually a prime candidate for stochastic optimization. Stochastic optimization means we're not going to use derivatives. We're just going to pick points at random and somehow improve our estimate. So how can we do Q-learning with stochastic optimization? Well, we have a number of choices that range from extremely naive to extremely complicated. A very simple solution is to just estimate the max with respect to a continuous action as a max over a set of discrete sampled actions. So you sample a set of actions, A1 through AN, from some distribution, maybe even a uniform distribution, and you just pick the biggest one. So this is the most naive way that you can stochastically maximize a function. Just pick a bunch of numbers out of a hat and choose the one for which the function returns the biggest value. This is dead simple. It's efficiently parallelizable because if you're using something like TensorFlow, for example, you can just sample all these actions, put them into one tensor, and evaluate the whole thing in parallel. But it's not very accurate. So especially as the dimensionality of these actions gets larger, your chances of actually finding an action that maximizes your value a lot is not as good. But do we really care about that? Like, how good does the target need to be anyway? You will get, if you include the action that was actually in the data into this set, you will get an action that's at least as good as what was in the data, so you'll probably improve on that. So you will actually get some sensible target values. And I should say, in practice, this thing actually tends to work reasonably well. There's a more accurate solution that you can have. You could, for example, use something like cross-entropy method, which is a simple iterative stochastic optimization procedure. We'll actually talk about cross-entropy method when we discuss optimal control in a subsequent lecture. You can use more complex algorithms like CMAES, which is an even fancier version of a stochastic optimization method. So we'll cover some of these as well. But they all have the same general flavor of picking some random actions, evaluating their values, and then if it's an iterative procedure, you sort of adapt your distribution from which you're picking those random actions. So that'll be for later. Generally, the sort of high-level bit when it comes to stochastic optimization works okay, maybe up to about 40 dimensions. If you're thinking about more than 40 dimensions, then you're probably in a bit of trouble. But up to about 40, it's okay. Now, there are other options, so I'll cover 3 options in total. Option 2 is to use a function class that is easy to optimize. So far, we've been talking about just using general-purpose neural networks that evaluate the Q value of a state and an action. We don't have to do that. We can actually constrain our class of functions to the class that is easy to optimize with respect to the action A. One very easy class of functions is functions that are quadratic in A. So we can have our network take in the state and actually output 3 values, a vector mu, a matrix P, and this matrix, maybe we output some low-rank factorization of it, and a scalar value V. And then we write down our Q value like this. It's a quadratic form using P and mu plus a scalar field V. And those of you that are kind of familiar with Gaussians will also recognize this as the equation for the log of a Gaussian up to a constant. So that's very convenient. Now, the nice thing about this equation, of course, is this is called normalized advantage functions, or NAF. The nice thing about it is that if you want to take the argmax, that's just mu, and the max is just v, because this value is quadratic, and there's a negative in front, so it's always negative. So the max will always be v, provided that your actions are unbounded. If your actions are bounded, then you need to do a little bit more magic on this. So this is a very convenient way to create representations for your Q function that can be maximized analytically without having to do any iterative procedure or any sampling. So this is another option that you have. The upshot of this option is that there's no change to the algorithm. You don't have to do any additional sampling. All you have to do is implement a different function for the max. It's just as efficient as regular Q-learning computationally. But the downside is that it loses representational power. So you can't represent Q functions that are not quadratic in A. In particular, if you have, let's say, a continuous action, but there's good actions over here and good actions over here, but bad actions in between, then you're in a bit of trouble because you can't actually represent this bimodal thing. So you lose representational power, but you gain computational efficiency and simplicity. Option 3 is to learn an approximate maximizer. And this is sort of the more complex solution, but the one that is a little bit more general than option 2. And this is described in an algorithm called DDPG by Lillicrap et al. From iClear 2016. So the algorithm is actually in the paper is described as a deterministic actor-critic algorithm, but we can also really interpret it as a kind of approximate Q-learning method. So here's the idea. Remember this way of writing the max? The max is just Q of S comma argmax of Q. Well, the trouble here is actually just the argmax, right? If we had some way to get this argmax, we just plug the action in and we evaluate the Q. So we're all set. So the idea here is this. Let's train another network, just a completely separate neural net, call it mu sub theta of S, such that mu sub theta of S is approximately equal to the argmax of Q. So we'll basically train a network to perform this maximization. This is often a solution in deep learning. If you're not sure how to solve a problem, just train a network to solve it for you. So we're going to do that here. We're going to train a network mu of S that approximates the argmax. And how do we train this network? Well, it looks like my clicker's out of batteries. Oh, there we go. Sorry about that. OK, how do we train that network? Well, we just need to solve this optimization. We have to set theta to be the argmax with respect to theta of Q phi S mu sub theta of S. And we can just do that with regular gradient ascent. So specifically, we can compute the derivative of the Q value with respect to theta just via applying the chain rule. So dA d theta, that's just differentiating through mu, and dq dA, that's just differentiating through Q. So we differentiate through Q, push that gradient back through mu, and that gives us a gradient of the final Q value with respect to theta, the parameters of that actor network. And now the target is just given by plugging in the mu for the argmax. So we just train a network to perform the argmax. So here is sort of the sketch of the DDPG algorithm, very similar to the DQN algorithm from before. Take some action, stuff it into your replay buffer, sample a mini-batch from your replay buffer, compute the target value using mu sub theta prime, actually, it's a target mu for the target. Update phi the same way that we did in Q-learning. And then update theta by pushing the gradient of Q through a mu. So you compute the gradient of Q, this is backpropagation, and then you backpropagate that again through mu. So you push that gradient through and you increment the parameters of theta with some other learning rate, beta. And then you update your phi prime and theta prime so that you now have two target networks. You have a target Q and a target actor. And you update them the same way, for example, using Polyak averaging. So that's the DDPG algorithm. It's pretty much exactly the same. The only difference is that in here you're plugging in mu, and in here you're updating your mu. So it's an approximate maximizer. Does anybody have any questions about DDPG or the other continuous action algorithms that I discussed? Yes. Okay. All right. There's a question back there.
Is your only one to run step 5 to completion, or does it just work if you give one step?
So there isn't any kind of like hard and fast rule. The DDPG algorithm as described in the paper takes one step. There's likely some complicated set of trade-offs as far as how many steps that you take there, but I'm not aware of any kind of detailed analysis of this. OK. So now let me conclude with a few kind of relatively simple practical tips for implementing Q-learning, and some of this might also be relevant for your homework. One of the things to keep in mind is that Q-learning type algorithms, especially continuous action algorithms like DDPG that introduce a second network, but even the standard discrete ones, they take some care to stabilize. And it's very important when you develop these methods to first test them on relatively easy, reliable tasks to make sure that your implementation is actually correct. So to illustrate this, these are some learning curves on different Atari games. This is from a paper by Tom Shaw et al. And you can see that on some of these games like Pong, there's very steady progress, and some of them are really, really messy. So make sure that you start off as you're developing your algorithm, test it out on relatively easy problems where you know that these methods are known to converge to make sure that things are really working, because if you just pick some arbitrary old problem, it might not necessarily be a good test for your algorithm. Large replay buffers do tend to help improve stability. So if you're training a network to play Atari games, a buffer size of like 1 million steps is actually pretty typical. And this basically makes the algorithm look more like fit a queue iteration. It sort of removes a lot of the dependency between the data gathering process and the training process. And in general, this kind of stuff tends to take time, partly because of the target network flipping, but also partly because the algorithm really does take time. So it's perfectly normal to see it not behaving much better than a fully random policy for a little while. So if you're like this curve for Pong, you'll actually be training a network to play Pong. And if you notice here in the beginning, this is sort of a very large number of steps. Here in the beginning, it's almost flat, and then it starts to pick up. So it's kind of an S-shaped curve. If you're used to training neural nets with supervised learning, what you usually see is a very immediate, very large dip in error, and then it plateaus. With these things, if you see more of an S-shaped curve, that's actually pretty normal. Generally, it's a good idea to start with high exploration and then gradually reduce it. So this was, I mentioned this before in response to a question, that early on your Q function is pretty lousy. So it's OK to start with a larger exploration rate and put it on a schedule so that it gradually goes down. A few more advanced tips for Q-learning algorithms. The Bellman error gradient can actually be pretty big. Remember that the Bellman error is squared error. So when you compute the gradient of that, the magnitude of the gradient increases the further away you are from 0. So this blue thing, this is squared error. It's a parabola, and you can see the slope gets bigger and bigger as you get further away. There are a few ways to mitigate the problems from this. One relatively simple one is simply clip your gradients. So if the gradients are larger than some magnitude, you clip them to that magnitude. An almost equivalent way to address this problem is to use what's called a Huber loss. So a Huber loss is a smooth approximation to absolute value. And smooth in the sense that close to 0, it looks a little bit like a quadratic, and far away from 0, the slope becomes constant. So that's the green thing there, and this is the equation for the Huber loss. So the Huber loss behaves extremely similarly to gradient clipping. So this might be a convenient way to deal with overly large gradients. Double Q learning helps a lot in practice. It's very simple, and it basically has no downsides. Like you need the target network anyway, so if you're going to have it, you might as well use double Q learning. At least if it has any downsides, I haven't seen them yet. N-step returns also help a lot, but do have some downsides. So generally, from my experience, there's not really any reason not to do double Q learning. There are reasons not to do N-step returns, but in practice, they can accelerate things quite a bit. Scheduling exploration and scheduling learning rates tends to be a good idea. So exploration should start out high and then gradually reduce. Learning rates, again, they can start out high and then reduce. Adaptive optimizers like Atom can also help quite a bit there. And then Q-learning, as well as actually many of the other algorithms that we've covered, they do tend to have a lot of variance between runs. So if you're debugging your algorithm or you're trying to evaluate how well your algorithm does on some problem, if you're running in a simulation, it's a very good idea to run multiple random seeds, because it's very easy to develop your algorithm until you happen to get one run that works and then stop. You say, oh, it's good, I got a good run. But what you're really doing is you're flipping the coin until it lands heads, and as soon as it lands heads, you're happy. So there's so much randomness in this that it's a very good idea, if you have the computational resources for it, to run multiple random seeds so that you know that the answers you're getting are really legitimate answers and you're not just waiting until you get good luck. OK, let's review what we covered. We talked about Q-learning in practice, how we can use replay buffers on target networks, and these things can help stabilize Q-learning and make it viable to use with large functional approximators like neural networks. We talked about how we can sort of generalize fit a Q iteration to subsume all the different variants of Q-learning just by considering these three processes: the data collection process, the target network updating process, and the training process. We talked about double Q-learning, which helps mitigate the problem of overestimation. We talked about multi-step Q-learning, which accelerates learning by using sums of rewards early on instead of cutting the trace immediately and putting in the target value. We talked about Q-learning with continuous actions using random sampling, analytic optimization, and a second actor network for approximate maximization. So this is Q-learning. And now, in the last 10 minutes of the class, I'm going to show you a few videos and talk about some papers that have used Q-learning in various interesting ways. So the first paper I'm going to talk about, this is Autonomous Reinforcement Learning from Raw Visual Data by Lang and Riedmiller. This is a paper from, actually the work, they had sort of their first paper in around 2009, but this particular one is from 2012. And this is a series of papers that use Q-learning in a latent space learned with an autoencoder. So their goal in these papers is to control, in this case, a little slot car. They have a few other examples like pendulums. So relatively simple low-dimensional systems from raw images. And the way that they're doing this is they're training an autoencoder to construct an embedded space, and then they're running Q-learning inside this low-dimensional embedded space. The way they actually, they use fit a Q iteration, and they actually do this, depending on the paper, they either use random trees. I think they do actually have one paper that uses neural nets, but mostly they use random trees. So it's a different kind of function approximator, but very similar algorithm, and then the neural net is used for the embedding. And we'll talk more about methods that construct embeddings later on in the course. So this is sort of one of the earliest papers that had Q-learning and neural nets, but the Q-learning was not actually with neural nets. This is a paper on playing Atari games. This is the Vlad Nee paper that was originally published in a workshop at NIPS and then in Nature. So in this paper, they used Q-learning with convolutional neural networks to learn Q functions directly from images without any kind of low-dimensional embedding. They use the replay buffers and target networks and perform a one-step backup. And this is a video of their learned policy, in this case playing Space Invaders, and you'll see a few other games in a second too. So one of the things that was really interesting about this paper also is that they demonstrated this algorithm on a very wide range of different games. So that was a very interesting way to kind of establish this as a benchmark for vision-based RL. There we go. Oh, and then takes one gradient step per experience step. The kind of results that were reported in this work can actually be improved quite a bit with a number of little tricks. So for example, double Q-learning actually will improve these results quite a bit. N-step returns will improve them quite a bit, and so on. This is a paper called Continuous Control with Deep Reinforcement Learning by Lillicrap et al. So this is the DDPG paper that I alluded to before. So this paper used continuous actions with a separate network to maximize the Q function. And it also uses a replay buffer and a target network, and then for the target network, they used Polyak averaging instead of copying it over every n steps. And they've demonstrated on a bunch of sort of simulated robotic-style tasks here. It performs a one-step backup and then has one gradient step per simulation step, just like the DQN work that I mentioned before. So here, a bunch of little simulated kind of robotic-y tasks. This is a paper called Robotic Manipulation with Deep Reinforcement Learning and Asynchronous Policy Updates, I think. This is by Gu and Holly, are the co-first authors. And in this paper, they use continuous actions with NAF, which is analytically maximizable, and they evaluate it on real-world robotics tasks. And one of the things here that's a little bit different is that the learning is actually parallelized across multiple robots, so you can see a second robot in the back, but that's just for data collection. So there's multiple robots collecting data, but then one learning thread that pulls that from the replay buffer and does learning. And also, since this runs in the real world, the data is a little bit more precious, so they actually take 4 gradient steps per simulation step to accelerate learning, because computation is relatively cheaper than data in this case. Okay, some suggested readings. A few classic, well, actually one classic paper. So this is the original paper by Watkins that introduced Q-learning. This is a paper by Martin Riedmiller that discusses using neural networks with fitted Q iteration. Some deep reinforcement learning papers. This is the one of the papers that uses this trick of embedding the observations into a latent space. This is the DQN paper. This is the double Q learning paper. If you want to read that in detail, they have a lot of good intuition for why this algorithm works well. This is the DDPG paper. This is the paper with NAF. And this is another paper that I didn't get a chance to cover that talks about a particular neural network architecture called dueling networks that actually separates out the value and the advantage term for the Q function that also produces considerable improvement in efficiency for things like Atari games. OK, well, that's it for Q learning. See you all next week, or on Wednesday.
So when you say that we expect like the reward to be equal to 200, is it like by the end of the iteration, or at some point when you have max iteration equal to 100, that's okay?
You're finding that it goes